So we're going to pick up like we talked about here where we just left off, and we were talking about really periodic trends. So we talked about the periodic table, and as we'll see in this experiment here today, a lot of these periodic trends are the reason why we see certain properties occur with metals and non-metals. And these are sort of the four sort of trends we're going to kind of really touch upon here: ionization energy, electron affinity, atomic radius, and electronegativity. Electronegativity is actually the only sort of thing that you'll need to know for the first exam from chapter 3. And really what you'll need to know is basically just the trend of it and sort of what it is. And obviously we'll use it a lot more when we get to chapter 3 in bonding. But that's, I think there's like a little spot that says like 3 point something. So that's really what from chapter 3 that you need to know for the first exam, as we'll talk about here today, the electronegativity. And like I said, when we get into chapter 3, we'll go into a little bit more detail and stuff like that. The rest of this obviously is from chapter 2. So we talked about effective nuclear charge just a second ago. And again, just to touch upon that one more time, this is really one of the trends why we see certain things develop in terms of atomic size, and also what electrons are involved in things like bonding, is really, again, as we can see with the simple example here of lithium, that outer electron is really not feeling as strong of a positive charge to the nucleus as those core electrons are, which is why, as we'll see here with ionization energy and things of that nature, it doesn't take a lot of energy to sort of remove those, because it's, again, furthest away, not being held as tightly. The other sort of effective nuclear charge, as I mentioned at the end there, is, again, as you sort of go to the right on the periodic table, you're building up a lot more protons, making that nuclear charge much more positive. And again, that's that overall positive charge going to bring everybody in a lot closer to begin with, rather than sort of to the left of the periodic table, where you don't have as big of a positive charge in the nucleus. So even though it's going to bring people in terms of those electrons, it's not going to bring them way in like you do as you kind of go to the right on the periodic table and build up that positive charge. The first sort of trend as well that we want to talk about is what is referred to as ionization energy. Ionization energy is the energy that's required basically to remove an electron from the gas phase of an atom. So it's really the energy associated with removing electrons. And as we talked about in a couple of places, when we remove electrons, something becomes positively charged. So a lot of times we look at ionization energy, and that is sort of what is associated with the formation of cations, which are positively charged because they do lose electrons. Now, when things lose electrons, it actually happens in a stepwise fashion. So things just don't drop off all 3 electrons at the first try. They do come off basically one at a time. And an example, as we can see there, is with magnesium. The first thing that would happen is magnesium would lose 1 electron, and that is why it's on the right-hand side of the arrow, like it's being given off and lost, so the product side of the arrow. And there's a certain ionization energy associated with that. And that is what is sometimes referred to as the first ionization energy. And that's the energy basically to remove the first electron, for example, here in magnesium. What would happen is after magnesium has lost that electron and has now become positively 1 charge, the next electron will actually come off, and we will lose 1 more electron. And that is what is sometimes referred to as the second ionization energy. And let's just say, for example, here, after it lost 2 electrons, it loses another one. That would be what is referred to as the third ionization energy. So in general, when we look at the first ionization energy, that is the energy required to remove really the first electron in an atom. And the general trend on the periodic table in terms of ionization energy is it increases as you go up and to the right, decreases as you go left and down. And that is really the first ionization energy. Is it easier to remove the first electron or the second electron? Which one is easier to remove? The first electron is a lot easier to remove because it is neutrally charged, right? So you're going to pop off that first electron. What happens when it loses an electron? Does the cation become larger or smaller? It does become smaller, right? Because it loses an electron cloud, so it sort of shrinks. that means the outer electrons that are further away are now finding themselves closer, right, to that positive charge, and are going to be held tighter, and it's going to be harder to remove the second electron, and then obviously the third electron. And that is what we see here with the numbers. First electron, you can pop off 735. Next one, about double, 1400. But now when you take that third one off, you need almost like 6 times or so the energy as the second one there to pop off that third one. And in the case of something like magnesium, it doesn't happen. And that is because when we look at magnesium's electron configuration of 1s2, 2s2, 2p6, 3s2, magnesium, which is group number 2, has how many valence electrons? 2. That would be these, right? So when you get to the third electron, you're now in the core electrons, yeah, much closer to nucleus, even closer at this point since you lost electrons, and it's just not going to happen for something like magnesium. And that's why magnesium will only typically make a +2 charge. Also why things like, for example, sodium will only make a +1 charge, because after you pop off sodium's first valence electron, you're now going to try to dig into those core electrons, and it's not going to basically happen. So just energy wise, it gets much, much harder every electron you pop off to try to pop off another one. And typically it's sort of doable through the valence electrons, but once you start reaching those core electrons, just energy wise, it's not efficiently enough to happen. Basically, it just takes too much energy to do so. Any questions on that there? So in general, as we go across a period from left to right, the first ionization energy increases. And again, what happens is electrons in the same principal quantum number do not completely shield one another from their nuclear charge. So in terms of shielding, as we were talking about, we have, for example, the lithium one that we were looking at. This valence electron is shielded by these lower electrons, but electrons that are in the same energy level don't shield each other. So it's just the shielding that happens from electrons that may be in a lower energy level than themselves. And again, because of that much stronger attraction, only those valence electrons really are the ones that get popped off. So in general, as we go down a group from top to bottom, as you talked about, the first ionization energy, I'll spit that out maybe. Ionization energy does decrease. Again, electrons are removed, are further from the nucleus. Again, as you go down a group, you also are getting a lot more protons, but that means you also have a lot more electrons. So overall, there's going to be a lot more electrons further away from the nucleus, higher energy levels, and a further distance. So even with that larger positive charge, it may not be able to bring them all in as close to hold them as tightly. So it takes a lot less energy to remove them. Here's sort of the trend as we go across the period. It's not a perfect trend, and that's also because of electron repulsions that occur. Again, electrons near electrons are going to be sort of away from each other, so we don't get a perfect sort of linear sort of line. So it's kind of jagged sort of pattern that occurs there, which is basically what we see there. All right. All right, so take a second here. Which atom would require more energy to remove an electron, sodium or chlorine? Which one should take more energy to remove it? Should be chlorine. Chlorine and sodium are in the same period on the periodic table, right? Chlorine is further to the right, which means it should have a higher ionization energy, and ionization energy is the energy required to remove the electron. Sodium should have a lower one, so it should be chlorine in this case, yeah. Which atom will require more energy to remove electron, lithium or cesium? So ionization energy decreases as you go down, right? So they are both in the same group. Lithium and cesium should decrease as you go down, and that should be lithium would require more energy, cesium would require less energy. Again, lithium, as we just saw, only has 3 electrons, right? So that outer electron is pretty close to the nucleus. As you go down, again, you have a higher positive charge, but you also have a lot more electrons and higher energy levels. So again, they're going to be further away from the nucleus and easier to sort of remove. Which one should have a larger second ionization energy, lithium or beryllium? Both in the same period. So let's think about it here. So lithium's electron configuration 1s2, 2s1, I think, right? Beryllium is 1s2, 2s2. How many valence electrons does lithium have? 1. How many valence electrons does beryllium have? 2. Second ionization energy means which electron goes out at that point? The second electron you're going to try to remove, right? When I remove the first electron from lithium, I am now in the core electrons, right? Which are going to be extremely hard to remove, right? When I remove the second electron here from beryllium, I'm still in the valence electrons, right? Which should be a lot easier to remove. So the higher second ionization energy should be our friend lithium, right? Because that is going to get you into the core electrons, which are going to be held a lot tighter than beryllium, still valence electrons, which is on the outer, right? So not held as tightly. Any questions on that? Right? And here's a chart of the ionization energies. Again, these are first, second, third, and fourth, all the way down, ionization energy. So here, sodium, we could see after that first valence electron, it's like a 10-fold jump in energy needed to try to rip off that second one. And that usually does not happen. And that's why something like sodium always makes a +1 charge. It will lose its valence electron. There's our jump we saw with magnesium, getting into its core electrons. Something like aluminum, you're okay, starts to increase, third electron increases. Then as you try to rip off the fourth electron and aluminum, that's a great jump in terms of energy, right? And it's not going to happen. Again, aluminum being 13, 1s2, 2s2, 2p6, 3s2, and 3s1, if I write the right there, 3p1, there we go. And in this case, it has 3 valence electrons, which are those, right? And once you get through those, you're now into those core electrons. And again, that fourth one, not going to happen. This is also, again, why we do see certain things on the periodic table that have fixed positive charges and some fixed negative charges as well. So for example, if everybody in group 1 on the periodic table will form a +1 charge when they do form ions. Everybody in group 2 will form a +2 charge when they do form ions. Group 3, which is pretty much aluminum, will be a +3 charge. And as you go kind of backwards there, you skip group 4, 5, 6, 7. Everybody in group 5, go there, -3, -2, and -1. And those are non-metals above the staircase. So it kind of goes +1, +2, +3, skip 4, -3, -2, -1 on the non-metal sort of side. A reminder as well, as we'll talk about a couple of times throughout the next chapters as well, things do not have charges unless they are combining with somebody, right? So if you have just something like sodium metal, it has no charge. If you have something like copper, it has no charge. Things only get charges when they combine. And really, they only get charges when they combine in ionic compounds, as we'll talk about in the bonding chapter. So just an element by itself does not have a charge. If you take anybody from the periodic table, uncombined, no charge, only gain charges when they have that. Transition metals, as we'll talk about, will have variable charges, but there are a few in the transition metals that have fixed charges. Zinc and cadmium have fixed charges of +2. And if you hang a left there, that's cadmium. Silver has a +1 charge. So those are fixed charges for those guys as well. Any questions on that there? Now, another trend is what is known as electron affinity. And electron affinity is different than electronegativity. Electron affinity is the energy that's associated with the addition of electron. It really is the energy change that occurs when somebody gains an electron. And when we talk about electron affinity and gaining electrons, it's really thought of as what happens when we make anions, which are negatively charged. And the general trend in electron affinity is as you go up and to the right, it increases on the periodic table. As you go down and to the left, it decreases. And it's not a perfect trend. For example, if you look at the halogens, it kind of increases, decreases, then increases. But in general, that's the general trend, sort of increases as you go up to the right and decreases go down. If you have an affinity for something, that means you like it. So as we go up and to the right, those are guys that typically like to gain electrons, right? So they're able to gain electrons. As you go left and down on the periodic table, those are guys that typically do not gain electrons. Now, let me just talk about this maybe here. Now, sometimes confused with this is what is referred to as electronegativity. And electronegativity is the ability of an atom to bring electrons towards itself. And on the periodic table, increases as you go up and to the right and decreases as you go down. The most electronegative element is fluorine. So fluorine is the most electronegative element you could have. It is also as far up and to the right as you could go, except for the noble gases, which frankly are happy the way they are. So they don't care about anything really. So that's as far up and to the right as you could go. And electronegativity is the ability to bring an electron towards itself, not to be confused with electron affinity, which is the energy change that occurs when somebody actually gains the electron. So one brings it towards itself so it can gain it. Once it gains it, talking about electron affinity and the energy change that occurs as opposed to being able to bring it towards itself. Now, all of these trends really do sort of help us understand as well the overall size that we see that occurs when we look at the periodic table. And by the way, since we talked about cations, what happens with anions in terms of their size compared to the neutral guy? When they gain electrons, do they become smaller or larger? The anion will become larger, right? So it gains electrons in its electron cloud. So in comparison to the neutral atom, when it gains a negative electron, the overall electron cloud gets larger, and the size of the anion is larger than the size of the neutral atom, while a cation, which loses electrons, shrinks, right? Because it loses those electrons, so it becomes smaller. Now, in terms of atomic size, as we touched upon, the trend that we see there is basically as we go up and to the right on the periodic table, the size gets smaller. So as you go on the periodic table, it decreases up and to the right, and the size increases as you go down and to the left. Bless you. So taking all these sort of trends into account is really why we see what occurs with metals and non-metals. So looking at sort of the chart here, as we go up and to the right, as you can see in this picture, we have a smaller size. Also, as we go up and to the right, we see the ionization energy increases and decreases as you go this way. We also see electron affinity increasing as you go up and to the right, decreasing as you go that way. Electronegativity increasing as you go up and to the right and decreasing as you go down. Effective nuclear charge increasing and decreasing. So what happens when we look at the periodic table is as you go up and to the right, you have things that are much smaller overall in terms of size. That means that the outer electrons are even closer to the nucleus and being held tighter, which means it takes a lot more energy to remove those electrons. And they really don't want to remove electrons because everybody's pretty much tight to one another. In addition to not wanting to lose electrons, they actually would like to take other people's electrons because they have that thing. They're small, big positive charge, going to bring electrons towards each other. All that means as you go up and to the right on the periodic table, these are things that like electrons to keep and gain. And that is really where we see our nonmetals on the periodic table. And that is why nonmetals typically will gain electrons, because they have all those periodic trends that basically favor that happening. It favors them bringing electrons towards itself, favors them accepting the electrons, also favors them not losing their own electrons. As you go down and to the left on the periodic table, you have things that are much larger in size, which means the outer electrons are not going to be held as tight. It also means that you don't need a lot of energy to remove those electrons. And frankly, because there's so many electrons and further away from the nucleus, they're not really interested in bringing electrons towards themselves. And you pretty much have guys on the bottom left or the periodic table that are okay with losing electrons. And those are typically where we find metals. And that is why typically metals will make cations, because they have all those periodic trends that basically encourage them to go ahead, take my electron, please. I don't really care. You could have it. And they will end up being cations, which are positively charged. And that's also, again, why our nonmetals will become anions, because they will take those electrons without a worry. Any questions on those trends there? Yeah. Okay. So let's talk about which one should be the larger atom, sodium or chlorine. Sodium should be the larger atom. Is further to the left. Sodium and chlorine are in the same group on the periodic table. Again, it has a much smaller positive charge, right? Which means it's not going to bring those electrons in as close as, say, our chlorine on the other side. Which should be the larger atom, lithium or cesium? Cesium should be the larger atom. It has a lot more protons, also has a lot more electrons, right? Which is going to build out the energy levels, right? And have a much more larger sort of atom that occurs. All right, so which one should be larger? Is it the hydrogen 1s orbital or the lithium 1s orbital? And which is lower in energy, the hydrogen 1s or the lithium 1s? So lithium on both? Let's see. I don't know about that. Hydrogen and then lithium. So let's see why this is, right? Hydrogen is 1s1, right? Lithium is 1s2, 2s1. Lithium and hydrogen, in terms of their nucleus, hydrogen has a +1 nucleus, right? In terms of protons, lithium has a +3 charge, right? So in terms of the 1s orbital, it's going to be drawn in, right? And it's going to be smaller than the hydrogen, which is not going to feel as much of that effective nuclear charge. And that's also why, in terms of energy, lithium will be larger. I'm sorry, lithium will be lower in energy because of the stronger positive charge. It will draw it in closer to the nucleus, and it'll be closer to the nucleus than, say, the 1s orbital there. And hydrogen, which is only feeling a +1 charge versus obviously a +3 charge. Any questions on that there? All right. These elements incur increasing ionization energy: oxygen, fluorine, and sulfur. Again, oxygen, fluorine, and sulfur are near each other on the periodic table. Looks like this on the periodic table. So in terms of ionization energy, increases as we go this way. So fluorine should be larger than oxygen, and decreases as you go down, which means sulfur should be less than oxygen because they're in the same group. So SOF. And in terms of atomic size, gets smaller as we go this way and gets larger as we go this way. So again, fluorine should be the smallest, followed by oxygen, and then getting larger going down the group to sulfur in that case. Any questions on that? All right, so we sort of talked about some of these things just to finish it up here, the last couple of slides. Again, the number of valence electrons is basically equal to the group number. It is also really important, obviously, in terms of bonding, as we'll talk about in the next chapter. You can, again, count off the electron configuration from the periodic table. And certain groups on the periodic table, as we talked about, obviously have special names, as we talked about there. There's the location of each of those guys. In today's lab, we're going to look at halogens, and I think some of these guys over here, we're going to look at those sort of activities. Now, if you had to take a guess here, based on periodic trends, where should I find the most reactive nonmetal? The top right of the periodic table is where I should find the most reactive nonmetal, which means they are all ready to gain electrons, right? So they're going to gain electrons. Most reactive metals should be found bottom left of the periodic table, right? Those are all guys that are willing to let go of their electrons pretty easily, and that obviously will allow them to be very reactive as well. All right, there's our divisions. We talked about our alkali metals. All right, so this does wrap up chapter 2.